In the previous video, we just finished discussing how we go about introducing symbolic data into our system. We do this by hooking functions such as read and replacing the concrete data that it introduces with symbolic data. We then allow the emulator to continue emulating, and as it operates over the symbolic data, it will propagate through the registers in memory. Eventually, what we'll see is that we end up with symbolic flags, and as a result, a symbolic instruction pointer. In this video, what we're going to look at is how we can use this to generate new inputs for the program. So, first of all, let's quickly run through an example of what it might look like when we emulate an add instruction. If we remember, we replaced the concrete data with these free variables that can just represent any value of a particular width, in this case 32 bits. So when we emulate an add over or involving symbolic data, what we end up with is something like this. So instead of getting a concrete value, we end up with an expression tree that represents what that value might be. Obviously, when we emulate instructions, we also need to figure out what happens to the flags. So for an add, we'll update the zero flag, the overflow flag, and so on, with something like this. An ITE is another type of abstract value that represents an if-then-else condition. So the condition for the zero flag is the result of the addition, in this case, equal to 0? If it is, then the ITE will take the value 1, otherwise it will take the value 0. And we also need to provide just a width for this expression, which is 1 in this case. So this is what will happen when we end up with flags that are set based on symbolic data. Instead of having a concrete value, so either true or false, or 1 or 0, they will end up being the result of an ITE. So that ITE represents how that flag was computed, and as a result we can figure out whether it's possible for it to be 1 or 0. So in this case it's quite simple. We have the add of two symbolic variables, then we have an and we say, is it possible that this computation is equal to 0? If it is, then the flag will be 1, otherwise it will be 0. So this is what happens behind the scenes in our emulator with add, sub, mul, so on and so forth, and for all the different flags involved. So we've just paused our emulator at a point in its execution where we have symbolic flags. So we can see in this case that the 0 flag is set based on the bitwise AND of the first byte that we introduced into the system with itself. So if we have a look at our program, it's quite likely that this is as a result of this check here, where we check to see if the first byte is 0 or not. If we look at the assembly of the program, we can see this is coming from here. We have a test of AL with itself, and then a jump based on that, where AL is derived from the first byte of user input. So what will happen at this point is when we have conditional or symbolic flags, the instruction pointer itself must become symbolic, because depending on the value of the flag, it will either take the jump or the fall through. So if we look in the code of our emulator, what we do on every different conditional jump type is we compute the condition. So for example here we see what we do on the JZ or JE. The condition is the 0 flag 1 or not? We then set EIP to be an ITE, where the condition is what we computed based on the flags. If that condition is true, then we go to the target, otherwise we go to the fall through. And again, this will result in is, instead of a concrete EIP, we have an expression that represents what the EIP might be. And depending on the conditions in that expression, we can either set it to be true or to be false. So here we can see what EIP is at this point. So again, keep in mind this is just after the test instruction. You can see that if the 0 flag equals 1, then EIP becomes this, which is the jump target. And if EIP is not 1, then it becomes this, which is the fall through address. So what we're going to do is we're going to take this expression and we're going to add a constraint. We're going to say that the result of this ITE is not this value or maybe not this value. And then we're going to ask the solver to give us a solution for that formula that makes the formula satisfied. Or in other words, provide an input to these values, or sorry, to this value here that satisfies the formula. What that will do effectively is it will provide us with an input that will make EIP be one value or the other. Or in other words, we're then using the solver to reason about the relationship between inputs and the path taken. So we do this here in our emulator or in our white box fuzzer script. We constrain the JCC for completion, which is just the EIP constraint, to be not equal to the taken address in the trace. So what that looks like is this. So in our concrete trace of the program, EIP ended up being this particular address. Which is the fall through. So what we're saying to the solver here is we don't want that result, we want the other one. So is it possible there's an input to this variable here that will result in this value coming out of the ITE, not this one? Which effectively maps back to asking the solver, is it possible that we'll end up at this program location rather than the fall through address? What we do then is we export this to SMT-lib format, which we just have an exporter for, and then reason about it with the solver. So back over here. We can see this is the formula that we create. Again, it's pretty simple because it's a fairly simple condition. But we have our ITE with two possible outcomes. So either EIP is this or EIP is this. And we're saying we want a satisfying solution to the formula that says this ITE is not equal to this value. So if a solution exists for this, the solver will provide us with an input or an assignment to this variable that results in this value in EIP. And that's effectively the core of what most white box fuzzing is about. The solver we're using here is Z3. And this is a very simple formula. So the solver quite quickly tells us that if you provide a 0 for that first byte, then instead of taking the path taken in the trace, the other path will be taken. So if we go back to our program, we can see quite clearly what will happen. In the original run of the program, this first byte was 0x41, so we ended up going in here. And the solver has just told us that if we provide a 0 for this value, we'll actually end up in here instead. So based on that, you can see how we go about doing input generation for a program and how we go about driving it down different paths. Slightly more complex is the second condition, where we take two D words from the program, or sorry, from the input. We add them together and we check to see if their sum is greater than 0x1000. In our original program, or in our original run of the program, we provided 0x41, 41, 41, 41. So the addition of that of itself is obviously bigger than OX1000, so we end up printing invalid. So we construct a formula for that condition as well, which looks like this. It's slightly more complex. We have 8 input variables representing the 8 bytes, and we have a variety of concatenations, extractions, and additions, just because when we read and write D words, we need to either break them down to their byte values or back up to their D words. So when we ask the solver, is it possible that we can take the other path here? The solver says yes, it's satisfiable. If you provide all zeros for these 8 input bytes, you will end up taking the other path, or EIP will have the other value. So we can see that's correct here. Instead of providing 41, 41, 41, if we provide all zeros, then the addition of 0 to 0 is less than OX1000, and we'll end up in here. So the white box fuzzer essentially just continues emulating every instruction in the trace. Every time it comes across an abstract EIP, what we know is that user input can control that or can affect that EIP, and we ask the solver to provide us with an input that results in us taking the other path rather than the one taken in the trace. To give a slightly more real-world example, one of the particular examples that I've ran this on is the WebP parser, which is just an image format. We can see here these 3 bytes are controlled by user input, and then we set a bunch of attributes on a structure, and then based on those attributes we take different paths. So it's quite simple, but it's slightly more interesting than our toy example. So in this case, the original trace provided a well-formed input, so we didn't take this error path here. So what has happened is when we reach this particular condition, we construct a formula which looks like this. We can see it has our 3 input bytes, and it's worth noting here that these 3, despite being indexed at 0, 1, and 2, are actually the 14th, 15th, and 16th bytes read in by the program. And we compare to 3 in 2 steps. First of all, we check to see if it's less than 3, and then we check to see if it's equal to 3. So what we're asking here the solver is, give us an input such that instead of this value being in EIP after this jump, we end up with this value in EIP. Or in other words, go down the other path. So if we ask the solver to reason over this, it again concludes that it's satisfiable, so it is possible to go down this path. And if we provide the value 8 for this input value, or this input byte, we'll end up taking it. So if we look at the code here, we can see this is correct. If bits is 8, shifted right by 1, we get 4, and with 7 is still 4, which is greater than 3. And we'll do the same thing for the next condition, and the next, and so on and so forth. And that kind of continues until we run out of conditions, or we run out of time, basically. And that's pretty much the core of how white box fuzzing works. We haven't discussed scalability or things like that, which turn out to be also quite important. But if you have any other questions or comments, feel free to either email me or drop a comment on my blog. And thank you.